Welcome to wrap-up video for lecture 15. I've written up here the problems I'm going to do at the back of chapter 15, which are 4 additional problems that are similar to the ones we did in class, but different. Go ahead and get your book because I did not type them up so that you see the problem in front of you. One thing you might want to do is now that you know what 4 I'm going to do, is try them and then come back, or watch one, then try the next one, and so on. Anyway, you get the idea. All right, we're going to start with number 40. It says a flask is charged with 1.5 atmospheres. So the first thing I'm going to do is write my equation. So N2O4, and this is a gas, in equilibrium with 2NO2 gas. All right, then it tells me that I have 1.5 atmospheres of N2O4 and 1 atmosphere, so those are my initials. My initial concentration, if this is 1.5, and my initial concentration of NO2 is 1.0 atmospheres. And you get the following. After equilibrium is reached, the partial pressure of NO2, so my equilibrium, is 0.512. So this is the type where you're given an equilibrium. So it's type 3, I believe, on my notes, where you are given an equilibrium and you're going concentration or pressure in this case, and then you're going to use that to get your others. And then, as the problem says, A, what is the equilibrium partial pressure of this? Well, we need to have that, okay, in order to be able to do B, which is calculate Kp. All right? And then C, we're going to switch that to a Kc. All right, so I'll put that over here. All right, so we'll get a little practice doing that again. All right, so what you've been given here is the X, the change. And the change is I went from 1.0 to 5.12. So I'm sorry, 0.512. Now this is a little bit different in that we are not going to be going to the right. The information given to us, this went down. So we must have shifted to the left. All right. So the amount I lost of NO2 is 1 minus the 0.512, which means that I lost 0.488. And if I lost this for NO2, I'm going to lose half of that for N2O4 because it's 1 to 2. So I'm going to lose half of that. I'm sorry, I'm going to gain half of that because I switched in this direction. It's a little different, all right? So I know what I started with and what I've added, all right? So my equilibrium concentration or my equilibrium pressure is 1.744. So I now have my 2 equilibrium values. So again, these were given initial. I was given the equilibrium pressure of NO2. Since it went down, it had to have shifted to the left, which means I added on the reactant side and subtracted on the product side. And so I added the half of 0.488 due to stoichiometry, and this is what I ended up with. And then to solve for Kp, I just take my products, squared for that 2 in front, over the 1.744, and I end up with 0.150 as my Kp. Now they want us to change that to a Kc, and our equation for that is Kp equals Kc times RT, change in moles, products to reactants, products minus reactants, so I've got 2 minus 1, so change in moles is 1, okay? All right, so then I'm going to say 0.15 equals Kc times 0.08206. The temperature given in the problem was 25 degrees, so I'm changing that to Kelvin times 298, and that'll all be raised to the first power. Solving, bringing that to the other side, I end up with a Kc of 6.15 times 10 to the minus 3. So this is a pretty straightforward problem. You're given one of the equilibrium concentrations, and that enables you to get the other equilibrium concentrations, and you plug that in to get your K. All right? Okay, we're going to do number 44 next. All right, next, number 44. All right, so reading from the book. How is a reaction quotient, that's Q, used to determine whether a system is at equilibrium? So if Q is equal to K, then the system is at equilibrium. So that's how we know. And remember, the only difference between these two is they solve them in exactly the same way. Is here you must put in, must have equilibrium concentrations. Okay. This one, you do not have, or you don't know if you have. Okay. So that's the difference between the two. All right, and B asks, now this is not really a problem, but I thought it would be good to go over it. B asks, if Q is greater than K, so Q is greater than K, how must the reaction proceed to reach equilibrium? They're both the same. They are a ratio of products to reactants. So if this is too large and you want to get to equilibrium, you have to make this ratio smaller. And in order to do that, you are going to have to increase your denominator. So make smaller, which means increase denominator, which means more reactants, which means shift left. Okay, in your equilibrium. C is the opposite. If Q is less than K, then this quotient must become larger in order to reach equilibrium. So you need to make it larger. So this is the thinking. Make it larger, increase numerator. Rather than memorize all the different types of problems, increasing numerator means shifting to the products. All right? And then at the start of a certain reaction, only that essentially C said, at the start of a certain reaction, only reactants are present, no products. So what is the value of Q at this point? Well, if I have no products, this is 0, and Q is 0, and so therefore Q is less than K, and what we just said about Q being less than K applies. So that essentially this question was asked, but it was asked in this way. So if I have no products, what is Q? Q is 0. So Q is definitely less than K because there are no negative equilibrium constants. So then you must shift towards products to bring it into equilibrium. All right. Moving on to number 50, which is actually a two-part, two different system question. Just does not want to let me do that. There we go. Okay. 50. A. At 800 K, the equilibrium constant 4, and here's my equilibrium, I've seen this before. Okay. Is Kc is 3.1 times 10 to the minus 5. Okay. If an equilibrium mixture in a 10-liter vessel, so 10 liters, contains 2.67 times 10 to the minus 2 grams of I, how many grams of I2 are in the mixture? Now it says if an equilibrium mixture, so this is at equilibrium, so I don't have any initial concentrations, but so essentially what we've been given a K, and we're going to be solving for one of the concentrations that we don't have. but I can't plug grams into the equilibrium expression. I need molarity. So that's where the volume comes in. And I'm going to be switching to moles using my molar masses and then using the volume to get to molarities, and then I can put it into the equilibrium expression. So taking the 2.67 times 10 to the minus 2 grams of I and changing it to, first of all, moles means I am going to be dividing by the molar mass, which for just one I is 126.9045 from the periodic table. When I do that, I get 2.104 times 10 to the negative 4 moles. And then I take that over 10 liters to get my molarity. So I'm going to put molarity down here. So that's what we're doing. We're changing these into molarities, which is equal to 2.104 times 10 to the minus 5. And that's what I'm going to put into my equilibrium expression. Okay? And then, so that this is x. All right? So Kc 3.1 times 10 to the minus 5 is equal to 2.104 times 10 to the minus 5 squared over x. Okay? Solving for x, or I2, I get 1.43 times 10 to the minus 5. Now I'll walk you through the steps quickly. All right, I took and squared this number, essentially cross multiplied and divided to solve for my x. All right, so, but they didn't ask what is the molarity of I, they asked how many grams. So now I'm going to take the 1.43 times 10 to the minus 5 molarity. So 1.43 times 10 to the minus 5 moles per liter times those 10 liters. Okay, and then get moles into grams, and this time I'm working with I2, so I'm going to take 2 times iodine's atomic mass, 253.81 grams per mole. Moles cancel, and I end up with the grams they asked for, and I got 0.0363 grams as my answer to A. Okay? All right, we're going to do B next. This one's a little tricky. All right, 50B says, and then gave you an equilibrium, 2 SO2 gas plus O2 gas gives us 2 SO3 gas. Okay? And it gives us a Kp. Put this down here. Kp equals 3 times 10 to the 4th. I'll tell you that I wrote it down as 10 to the minus 4 and had to figure out why I wasn't getting the right answer. 700 K. This is important in this one. And it's a 2-liter vessel. Now, in a 2-liter vessel, the equilibrium mixture contains, so it gives us equilibrium concentrations again, but they're not in molarity. They're in grams. 1.17 grams of the SO3 and 0.105 grams of the O2. How many grams? So it's very similar to the previous problem, but this has got a little twist. We cannot do what we did in the previous problem. We cannot change these to moles, take the 2 liters, change it to molarities because we have a Kp. Now, I guess we could do that if we change the Kp into a Kc, but another way to do it, if we're going to stay with the pressure, is to change these to atmospheres, because I can only put pressures in for a Kp. Now, how am I going to do that, you ask? I am going to use our handy-dandy ideal gas law. And I am going to get moles from those grams, and I'm going to be solving for pressure. So pressure equals nRT over volume is 2, temperature 700, there's our gas law constant. All I need to do is change these grams into moles using the molar masses. So for SO3, taking 1.17 and dividing by all of this sulfur and 3 oxygens together weighs 80. So 1.17 divided by 80 gives me 1.46 times 10 to the minus 2 moles. And I'm just going to kind of put it here as a number on my way to atmospheres. So it's going to be that number of moles times R times the temperature divided by volume. Okay? When I do that math, I get 0.42 atmospheres. Now, if you want to make sure you got that, then stop the video and make sure, okay, that you can get those number of moles and plug that in to get the pressure. All right? I'm going to do the same thing for oxygen. It weighs 32. The number of moles on my way to atmospheres is 3.28 times 10 to the minus 3 moles. And again, you're going to take moles times R times T divided by volume, and you're going to end up with 0.0942 atmospheres. And what I'm actually going to put into the equilibrium expression are pressures. So when I solve for X, it will be in atmospheres. Now, when you are given equilibrium, we talked about this in class, this type of equilibrium problem. When you are given equilibrium concentrations or pressures, you do not use stoichiometry here. Plug them into the K expression, solve for X. Right? So 3 times 10 to the 4th equals SO3 on top, but squared, so 0.42 squared over 0.0942 for oxygen, 0.0942 times, now I will square the X, okay, because it's X squared, all right. When I take this denominator here and multiply it times the left-hand side of the equation, I get 2.83 times 10 to the 3rd X squared equals 0.176. This came from here, and that I got this by taking this times that. Okay? All right, so I'm essentially cross multiplying and dividing. And now I need to get X by itself, so I'm going to say X squared equals, it'll be 0.176 divided by the 2.83 times 10 to the 3rd. And I get 6.22 times 10 to the minus 5. And then when I take the square root of that, I get a little more room here. I get X is equal to 7.89 times 10 to the minus 3 atmospheres. Right? They did not ask for the pressure at equilibrium for SO2. They asked for the grams. So I am going to go back to my ideal gas law, and this time I've got my pressure, so let's write it down. PV equals nRT. I have pressure, I have volume, I have this, I have this. I'm going to be solving for moles so that I can get to grams. Okay, so nRT, N equals PV over RT. Plugging in my pressure, 7.89 times 10 to the minus 3 times my volume, which is 2, divided by my R, times my temperature, 700. I get number of moles I get is 0.74 times 10 to the minus 4 moles, and then converting that to grams, SO2 weighs 64 grams per mole, and I end up with 1.76 times 10 to the minus 2 grams. All right, answer for B. So that was 2 different problems under one, so you kind of got a twofer. All right, our next problem, and is it our last? Yes, number 60 is our last, but let me just make a comment here. Let me get another page. Oh, let me do it right away that time. Number 54, as I was looking through, trying to decide which ones I was going to do, Number 54 and number 58. I mean, I try to get, ones that reinforce what we did in class, but nothing too close. 54 and 58 are very similar to 56 that we did in class, to number 56, all right, which I think was number 11 in the practice. All right, our last problem is number 60, and yes, we're going to do the quadratic formula one more time. All right, let's read that one. It's one of those that looks long, but it's not bad. I mean, in terms of how much you have to read for the problem. All right, so it says, the reaction of an organic acid with an alcohol in an organic solvent to produce an ester in water is commonly done in the pharmaceutical industry. It's also commonly done in your body as a very common reaction in biochemistry. This reaction is catalyzed by strong acid. A simple example of the reaction, so let's write our equilibrium. Now we have encountered this reaction before when we talked about polymer solids. So when you take two things and stick them together by taking water out, this is called a condensation reaction. And that's essentially what we're doing. We're taking H off the acid and OH off the alcohol to make the water, and you stick the two pieces together. So CH3, COO, and then CH2, CH3. And this is called an ester. All right, so there's our equilibrium, okay? And it says that all of these are SOLV, which means that they're all dissolved in a liquid, even the water, but they're not aqueous, so it's an organic solvent. So we are going to include water because it's not pure liquid. It's dissolved in this organic solvent. Okay, the equilibrium constant for the reaction is 6.68, and I'm assuming it's a Kc, they don't say. A pharmaceutical chemist makes up 15 liters of a solution that is initially, so we get to do our ice table, that is initially 0.275 in acetic acid, 0.275 molar, and 3.85 molar in ethanol. And you have no products to begin with. All right. At equilibrium, how many grams of ethyl acetate? So, one little tricky bit is that you are not going to use this volume until the very end. We are going to set up our ice table. We're going to put it in the equilibrium expression. We're going to get a molarity out for the, how many grams of ethyl acetate? That would be this one, not the acetic acid. Okay, so that's our question. But when we solve the equilibrium expression, we're going to get a molarity, and then we're going to use the volume and the molarity to get to grams. Okay? All right, so that's a little bit tricky. All right, so we have no product, so we know it's going to shift to the right. It's all 1 to 1 to 1. So these two over here, these two products are going to be plus X, and these two are going to lose the same. Everything's 1 to 1 to 1. So it's all minuses and plus X's. So at equilibrium, this is going to be 0.275 minus X, 3.85 minus X, and then this will be X, and this will be X. All right, so Kc, which is 6.68, is equal to products X squared, X times X, over 0.275 minus X times 3.85 minus X. All right, so we got to do our binomial expansion here. Okay, when I do that, I'm going to say, okay, so 6.68 equals X squared, factoring out the denominator, I get 1.06 minus 4.13X plus X squared. Okay. Now I'm going to take this whole thing and I'm going to cross multiply. So I'm going to multiply it times 6.68. When I do that, I get 7.08. So 6.68 times 1.06, 7.08. Collect 6.68 times 4.13 minus 27.6x, that's a point, plus 6.68x squared equals x squared. All right, collecting my terms, bringing that x squared over, I end up with C for my quadratic formula is 7.08, B is a negative 27.6, and A is 5.68 because I subtracted x squared from both sides, and that is equal to 0. Quadratic formula, drum roll please. Opposite of B, 27.6 plus or minus the square root of B squared, which is 27.6 squared, which is 762, minus 4AC, so 4 times 7.08 times 5.68, and that comes out to 161, all over 2A, 2 times 5.68, 11.4. All right, so now we're going to take our plus and minus roots. The plus root is obtained by taking 27.6 plus, so let me just simplify this one more time, 27.6 plus or minus, when I take the square root of that, do my subtraction and take the square root, I end up with 24.5 over 11.4. So my plus root is 27.6 plus 24.5 divided by 11.4, and that comes out to 4.57. My negative root, when I take 27.6 minus 24.5 divided by 11.4, I get 0.272. All right, now go back up here to your ICE table, and which of those two roots makes sense? Well, 4.57 wouldn't make sense here. Or here, you'd end up with a negative concentration, so it is the negative root that we're going to use. And X is 0.272 molarity, okay, which is what my product is equal to 0.272 molarity. Okay, scroll over just a little bit. So for ethyl acetate, which its amount at equilibrium was X, it is 0.272 moles per liter. They wanted grams, not the concentration, times those 15 liters, times the molar mass of ethyl acetate. If you add all of that up, the CH3COOCH2CH3, you end up with, what did I get? 88.1 grams per mole. And when I do the math, I end up with my answer, and I'm going to write it right up here, 359 grams. That pretty much is all of the numerical type problems for this chapter. I guess I could do one more Le Chatelier. Let me see if I can find one quickly. Okay, we did 64. Let me just talk about 67. It's short, and at least will give us a little bit more practice with that, and then we'll end our little video. Okay, so one more blank page, please. Thank you. So 1567, I know you have the answer, but that's okay. We'll just go over it anyway. 203 gas is in equilibrium with 302 gas. Would an increase in pressure favor the formation of ozone or oxygen? So when you were looking at pressure increases, you want to look at gases. And I see 2 gases, 2 gas goes to 3 gas. An increase in pressure means you have less room for particles. So you want to shift to the side that has fewer particles, so you would shift to the left. A decrease in pressure means you would shift to the side that had more particles, so you would shift to the right. If you had an equal number, then changes in pressure would not make a difference. Let me just throw in some heat here, since that seemed to give y'all some trouble. Number 66 asks you to calculate the delta H of the reaction that's there using the Appendix C that you used in 131. If I can look that up really quick, we can go over that to give you a change in temperature. So let me just write it down, and I will look up that delta H really quick. All right, plus 2H2. All right, so let me look that one up, 66. All right, the delta H is negative. So if you calculated it, the delta H would be negative 90.7 kilojoules. Now, which side are we going to write the heat on? It's exothermic. Exiting the reaction means I am going to put that heat, or that 90.7, right here. All right, so let's see what it says. B, to maximize the equilibrium yield of methanol, would you use a high temperature or a low temperature? All right, well, if I put heat in, then it will shift my equilibrium to the left, because the heat's on the product side, it'll shift it to the left. So I do not want to put heat in, I want to take heat out. If I take heat out, then it will have to shift towards that removal, so I want a low temperature, and that's B. All right? Put the heat on the right side and then play around with taking it out and removing it to see how it shifts. And then C on this same problem says, to maximize the equilibrium yield of methanol, would you use a high or low pressure? High or low pressure? Well, I see 1 plus 1 gas particle here for CO, plus 2 for H2, so that means I have 3 gas particles in equilibrium with 1 gas particle. So if I want to maximize my yield of product, then I definitely want a low pressure, which will shift me towards the side with fewer particles. So low pressure, low temperature for this equilibrium. And that is going to conclude our